Chemical formulas. So we've got all these different compounds. We have to represent them. There's lots of different ways to represent compounds, but we've come upon, or we've gotten together and decided upon a system so that each compound has a chemical formula. And that represents the different elements that are in the compound and the relative number of atoms or ions that are in that compound. So we use the element symbols to indicate which elements are in there, and then we use a subscript after the element symbol to say how many of that particular element. So water, we've talked a lot about water, and there's 2 hydrogens for every oxygen. We've got the little picture of the red and white Mickey Mouse heads. H2O is the symbol, the chemical formula for water. H2 means there's 2 hydrogens, and O means there's 1 oxygen. Chemists often leave the number 1 out. We don't write it unless we really have to. So here we don't write H2O1 because if it was more than 1, if it was 2 or 3, we'd write that number. And if there was 0, we wouldn't write the O at all. So the fact that we wrote the symbol once means there's 1 of them. Carbon tetrachloride is another compound, and that's represented as CCl4. So there's 1 carbon and 4 chlorine atoms. And this is an example of why you need to be careful how you write your lowercase l's. Okay, I think I mentioned this. I changed the font that I used on my PowerPoint slides because the previous font, lowercase l's capitalized and the number 1 looked the same. And so if you're doing that, then you end up with something like this, C, C. Okay, now is that a capital I? Is that 4 iodines? Or is that a lowercase l? Part of the Cl is that chlorine. So when I write these out by hand, carbon and chlorine, I always write my lowercase l's as sort of a cursive L to just make it clear that I'm meaning an L and not a capital I. If this was a capital I, though, we do have a clue that something's not right, because we wouldn't write carbon-carbon. We'd write C2I4, if that's what we meant. So that's kind of a clue. But you have to be careful when you're looking at these formulas. And that's why it's very, very important that your capital letters be large, and the correct form for capitals, your lowercase letters be small, and they be actual lowercase letters and not just small capital letters. There are different types of chemical formulas used to represent the same compound. And we have them because they're useful in different situations. So we can categorize them into 3 different types: empirical formulas, molecular formulas, and structural formulas. So an empirical formula gives the relative number of atoms for each element in a compound. The word empirical means by experiment. So this is the sort of formula that we would get from an experiment. And we're going to do an experiment like that in lab. I think it's next week, where we actually determine the formula of a compound. Empirical formulas show up a lot in general chemistry classes. We need to know what they are. Once we get past that understanding of what an empirical formula is, we actually don't use them all that much. But because we're in a general chemistry class, we do have to study them. So hydrogen peroxide, its empirical formula is HO. But the actual molecule has 2 hydrogens and 2 oxygens in it. I was trying to come up with a joke about Santa Claus, but I decided not to. So this is the actual molecular formula. We'll talk about that in a minute. This is the empirical formula. It's the lowest ratios. It's the relative numbers. So 2 hydrogens to 2 oxygens, that's a ratio of 2 to 2 that can be simplified to 1 to 1. So this just gives us the lowest ratio, the relative numbers. The molecular formula is much more useful. This is the one we use most of the time. It gives the actual number of atoms of each element in a given molecule. So we have some examples here. So C4H8, okay, that's the molecular formula for a compound. From this, we can write the empirical formula. We look at the numbers 4 and 8, and that can be simplified. 4 to 8 ratio can be simplified to 1 to 2. There's a common factor in each of those of 4 that we can factor out. So the lowest ratio is CH2. There are actually a host of compounds that have that same empirical formula, the ratio of carbon to hydrogen 1 to 2. So this is an empirical formula. I'm sorry, this is the molecular formula. That's the empirical formula. Here's another one, B2H6. From this molecular formula, you should be able to figure out what the empirical formula is. Just find the lowest ratio. 2 to 6 simplifies to 1 to 3. For carbon tetrachloride, CCl4, that's a ratio of 1 to 4. That is already in its lowest form. And so here the empirical formula and the molecular formula are exactly the same. That can happen. The empirical formula for water is the same as its molecular formula, H2O. Those numbers cannot be reduced. Any questions about that? Then a structural formula gives us information about the structure of the molecule. This helps us to understand how the atoms are connected. This molecular formula, C4H8, doesn't give us any information about how those pieces are put together, just that they are all together. So in the structural formula, we represent covalent bonds as lines. There are single and double and triple bonds, and so we represent those as a single line for a single bond, a double line for a double bond, and a triple line for a triple bond. Let's just give an example here. So for carbon tetrachloride, a structural formula might look like this. Where all 4 of the carbons are attached to the carbon, all 4 of the chlorines are attached to the carbon with a single bond. And we'll learn more about that. For some compounds, there can be several different structural formulas with the same molecular formula. So which formula we use depends on how much we know about the compound and what we're trying to communicate. Structural formula gives us the most information. Empirical formula gives us the least. So write the empirical formula for the compounds represented by these molecular formulas. So if the molecular formula is C5H12, what's the empirical formula? It's the same, right? C5H12. Those subscripts have to be whole numbers. A ratio of 5 to 12 cannot be simplified. There's no common factors. How about Hg2Cl2? HgCl. The lowest ratio is 1 mercury atom to 1 chlorine atom. How about this one, C2H4O2? Yeah, all of those subscripts are divisible by 2, and so we can simplify this to CH2O. Okay, questions? We also use molecular models, and we've already used pictures. Those are molecular models. It helps us to get a better understanding of the shape of a molecule. It's more accurate than just the formula. We tend to use these colors to represent these atoms, these different elements. You do not need to memorize this list. But in the book, we're going to be consistent, and whenever you see a red ball, it's oxygen, a white ball is hydrogen, etc. So it's color-coded. This is not necessarily a universal color code, but it's one that's very commonly used. So we can make a ball and stick model where we represent the atoms as balls and the chemical bonds are sticks, kind of like scientific tinker toys. and we can represent how these things connect to each other. So this is an example of a ball and stick model. So this is a space-filling model, which is more closely representative of the actual shape of the molecule. It's very convenient, and I would encourage you to think of atoms in this way because it's easier to get our minds around, and it's clearer to look at a model like this. That's why we use them so much, is because it's open and we can see through and what's on the other side. But that molecule actually has more of this shape. The atoms, when they bond to each other, they kind of blend into each other a little bit. They squish together. So this helps us to understand the true shape of the molecule, but it's difficult to draw and it's difficult to look at. So here we have several different ways to represent the same molecule. So we can call it, right, CH4, that's the molecular formula. Here's the structural formula, just showing how they're attached. It's not giving any information about the actual shape of the molecule. The ball and stick model gives us the attachments and the overall shape, and then the space-filling model is the most representative. Any questions? I will never, ever ask you to draw a space-filling model. I would not want to try that myself. You may need to draw one of these, though. This is a table from your book just showing these different types of formulas for several different common substances. Let's look at glucose. This is the sugar that's in your blood. So here's the actual molecular formula, here's its empirical formula, and here's its structural formula. Here we can represent it with balls and sticks, and when we do the space-filling model, you can see that it's difficult to figure out exactly how many things there are because some of the things are hiding on the back. What, this one, the structural?
The glucose, the ball and sticks, or the space filling seems easier than the...
That seems easier to draw?
Because less detail, just draw a blob.
Well, yeah, but you have to know where the blobs go. That's the tricky part. For those of you that are interested, glucose is one of a long series of hexose sugars. They all have 6 carbons. And the difference between the sugars is extremely subtle. It has to do with the exact geometry around these carbons. And I mean, it's just mind-boggling, but your body is very aware of the differences between those sugars. That's getting into biochemistry, which is really, really fascinating. So here we see some double bonds in benzene, and here's a triple bond. And in this one, we have some single bonds and a double bond. Here's ammonia. There we see the blue ball for the nitrogen. Any questions? You don't need to memorize that. That's just to show you, how these different things are represented.